Welcome back to our series on multivariable calculus. In this episode, we're going to talk about substitutions, but not the kind of substitutions we've been looking at recently. That is, substitutions into cylindrical or spherical coordinates from Cartesian. Instead, we want to talk about a more general substitution. That is, a substitution similar to what we did in Calculus 1. Let me give you an example. If we wanted to integrate e to the 3x minus 2, the first thing we would probably do is perform a u substitution in order to build exactly what should be under the integral for the integral to be simple. Because e to the u is a simple integral, I'll try the substitution that u is going to be equal to 3x minus 2. That means du, the derivative of this, which really represents du dx, is just going to be 3 dx. That means dx itself is going to be equal to 1/3 du. Well, now I'm ready to make the substitution. The only thing that's lacking are the limits. Now, you learned in Calculus 1 that you could go ahead and do the substitution, perform the indefinite integral, and then convert back using your reverse u substitution and use the old limits. But let's go ahead and replace the limits as well. You might not have done this before, but it'll be pretty important for the substitutions we're about to engage in. So what we want to do now is actually look at what the u limits would be under the conditions of 0 for x and 3 for x. So I'm going to call the first one u0. When x is equal to 0, u is actually equal to -2. So that will be the lower bound of our integral in u. The next one defined is u of 3. When x is 3, this is going to be 6 minus 2 or 4. So the upper bound will be 4. That way I can rewrite the entire integral, not just the argument for the integral, the integrand, but I can rewrite the limits too in terms of our new substitution. So I have had to make 3 substitutions here. I've had to substitute for the differential, I have to substitute for the argument, and I have to substitute for the limits. It's important we look at all 3 of those because that's the kind of substitution we're going to do now. Let's go ahead and complete the substitution, but we're not going to complete the integral. This will now be the integral from -2 to 4 of what e to the 3x minus 2 is will be e to the u, and I'll replace dx with 1/3 du. And now we're ready to complete the integration. Plug in the limits, and we'll end up with the same answer we would have gotten with the original. Okay, now we're going to do a substitution of a 2-dimensional integral. This is going to involve 2 substitutions, not 1. And unlike before, we were really just making that substitution in order to turn an integrand into an easier function so that we could take the integral easier. There are lots of reasons why we might want to substitute in for this function z x of y. It might have to do with the limits of integration, or it might have to do with the difficulty of the integrand in x and y. There are a number of reasons why substitutions are preferable. Let's take a look at a substitution with this 2-dimensional integral. Well, just like before, we're going to need functions to substitute in for our variables. So what we're going to do is say I'm going to replace x's with f of u and v, where u and v represent my 2 new variables that I'm replacing x and y by. Y then will be a function g of u and v. The selection of these functions you can only gain after some experience. Just like with our 1-dimensional answer or example, you knew to replace 3x minus 2 with u because you'd done u substitution before and you knew that would simplify the integrand. Well, with experience, you'll be able to select these functions f and g. We'll even look at a few examples of how previously used substitutions are valuable and how they kind of fit into this model. But just know for now, most of your early problems in substitutions, they're going to provide you with the substitution functions. You won't be coming up with those on your own. Okay, well, now that we have the substitutions, we've got 3 jobs to do. Same 3 jobs we had before. I'm going to have to rewrite the function z that was in x and y in z in terms of u and v, and I will use these substitutions to do it. I'll have functional relationships between u, v, and x, u, v, and y, and I'll use those to make that substitution. I'll need to do the same thing with the limits of integration. That is, I'll have to utilize the fact that I know the limit values on x and y and use those to determine the limit values on u and v so that I can rewrite this in terms of integrals in u and v. My final task is to replace the differentials. And you might think that's easy. That is, replacing the differentials won't be any more difficult than either of the first two steps. But it turns out to be the trickiest of the three. Just like when we did the one-dimensional example, it turned out that du and dx were not equal to each other. Du was actually a functional relationship to dx. It turned out in the last example to be that dx was equal to 1/3 of du. And that's generally always the case. When you change variables, your differentials change the size of the area elements that you're integrating under. Let's take a look at an example. If we're originally indicating our integral in Cartesian coordinates, then we've got an x-axis and a y-axis, and that means we've got a small rectangular differential space, and it has dimensions of dx by dy. That's going to give this an area of dx times dy. Well, we're going to replace this space with a new space, and that new space is going to be defined in terms of u and v. Now, I don't know that u and v form these perpendicular axes that are going to still form rectangular pieces. After all, think of polar coordinates. Our new variables r and theta form these concentric circles of various different radii that we use a theta value to indicate how far we are along the arc length. So I'm just going to basically simulate that this forms a new rectangle, but understand this rectangle in this position isn't necessarily what u and v are actually going to form in terms of differential areas. So this just represents an example of what they could look like, not what they actually look like. So this would be the differential du, and this would be the differential dv. It still represents a little area unit, but the product of du and dv is not going to be the same size as dx dy. So when I go to replace dx dy in my substituted integral, I need to replace that with the proper size conversion for du and dv. To figure out what that is, I actually need to find the size of this area. And it turns out I can do that. If you'll recall, we can always find the area of a parallelogram by knowing vectors that run on two sides of the parallelogram and taking their cross product. And I happen to know the two vectors that lie on each side. Because I have functional relationships for both the x and the y, I can take partial derivatives of these functions, and those will indicate the lengths of the sides of this parallelogram. So first, in the du direction, I'm going to have a vector that's horizontal like that, and that vector is going to be the partial derivative of f and g in terms of u. So this is going to be f of u, g of u, and 0. It doesn't go up or down. And of course, to adjust its length, I'm going to multiply it by du, and that way it'll be a variable length chosen by the size of my differentials. It won't be fixed to be the length that this vector actually comes out to be. Well, vertically, I have one that runs in the vertical, or dv direction in this case. And of course, I can get partials for f and g in terms of dv, and that will indicate the length of that vector. This one's going to be f of v, g of v, and 0. And just like we did with the du, we'll multiply this by dv so that it will provide a variable length for the side, so I can change it from a larger or a smaller. But the proportion of one side to another is fixed by my selection of the variables and the relation of those variables to x and y. So these two vectors will definitely give me the area of this parallelogram, and then I can compare it to the area of the dx dy. What I really want is to make a statement of the product of dx dy equals some function times du dv. And I'm going to get this function by actually solving for what the area of this parallelogram is. And of course, the area of the parallelogram is the result of the cross product of these two vectors. So let's do that. Well, I know I can cross product two vectors by starting with a top row of ijk, and then under it, I'll put the first vector in the cross product. And this will be du crossed with dv. So it's going to be fu, gu, 0. And the bottom line is going to be the other vector I'm taking the cross product of. It's fv, gv, and 0. And then I'll just keep in mind after I do the determinant of this 3 by 3 to find the cross product that what I really want then is the absolute value of the cross product, because the cross product could be plus or minus based on the direction these vectors actually point. And of course, I always want the area to represent a positive number. So I'll just remember to take the absolute value when I'm finished. In addition, of course, I'm going to multiply du dv at the end. They're sitting right here, and they don't have to participate in the cross product because they're just scalar multiples. Okay, let's do the cross product. Well, because the k column is 0, it makes it really easy. I don't need to worry about the I component of this vector because the cross product is going to be 0. I don't have to worry about the j component of this either because the cross product will be 0. This only has a cross product for the k component. And that makes sense because if u and v represent I and j, I definitely know that the vector indication, the cross product that's going to indicate this area, will be perpendicular to both. So it should be coming out of the board at me, and in fact it is. So the k component is actually going to be equal to FUGV minus FVGU. And of course, I want the absolute value, that is the size of this particular vector that indicates the area. That's what goes right here on this blank. It's FUGV minus FVGU. And I throw absolute value signs around it just to ensure that it's never ever going to be negative because it's representative of an area. And there's our answer. If I know the substitution formulas for u and v into x and y, then I can simply take the magnitude of their cross product, and that's going to provide me with the conversion factor between the differentials. This has a special name. It's done so commonly every time you convert from one set of parameters to another. This is called the Jacobian. And the Jacobian is how we write a two-dimensional integral in another set of variables where the variables don't have a standard geometry. Of course, we already know how to convert a rectangular set of coordinates into polar coordinates. We could take it and convert it into spherical coordinates, and those are very familiar to us. But what if we want to convert it into coordinates that are non-standard? I want to use a u-axis and a v-axis without necessarily using those as standard axes that are going to be used in multiple problems. This u-v axis may only be suited to solve this one problem, and so it's not worth inventing a new geometry for. It's just worth utilizing it to solve this problem. You'd be surprised how valuable these alternative geometries are for taking what would be impossible integrals to evaluate and transforming them into an integral that's easy to evaluate. You'll get lots of practice with these. As long as you can calculate the Jacobian, you can then convert the z function into its new values in this new geometry. And then finally, rewrite the limits of integration for u and v. These problems will be no different than any other double integral.